I'd like to welcome Dr. Prathap Parameswaran, Associate Professor of Civil Engineering and one of the recipients of the 2021 Global Food System Seed Grant. Dr. Parameswaran.
Hi. Well, thank you for that introduction, Maureen. And hello, everyone. So today I'm going to be presenting the final outcomes of our research that we were able to conduct thanks to the Global Food System Seed Grant Award of 2021. And the title of our talk today and the project itself in general is Leveraging the Circular Bioeconomy, Sustainable Recovery and Optimization of Slow-Release Biofertilizers from Livestock Wastewater. This has been an initiative that has been a topic of great interest for myself and a team of cross-college disciplinary faculty, academic, and industry interests to promote the concept of circular economy as it applies to agricultural activities, agricultural economy, and to even other aspects of society. So my co-PI on this project is Dr. Ganga Hetirachi, who is a professor in the Department of Agronomy. Ganga and I have been active collaborators on this topic, and it's another example of how trans and cross-disciplinary research is really essential to bring the outcomes to fruition in the real world. And so we will have at least two examples of where or how we are working towards those goals through today's talk. So let me just introduce you the major problem and the subset of the opportunity or the subset of the greater agricultural sphere that we are in, and zone into livestock and ag wastes specifically. So our world begins with wastes, which is an essential aspect of any agricultural activity, be it crop production or animal agriculture. And so our interests here are pertinent to the livestock industry, specifically livestock waste. And so to the far left of this slide, you can see the prevalence of these animal waste. And you can immediately catch the attention that there is a bullseye of the quantities that are generated right along the heartland of the country, especially along the Ogallala Aquifer and spreading out into other parts of Midwest, especially when it comes to beef or cattle feedlot operations. And in the case of swine industry, there's also a local concentration, if you will, in the upper Midwest into the central part of the United States, and also a sublocal concentration in the Carolinas. But again, a key point to note is these are not distributed across uniformly throughout the country. There are regions where they are generated in huge quantities, which also puts Kansas right under the roadmap. So that is a problem in terms of the amount of waste that is generated. And the current disposal practices are minimal at best or very conventional. And the methods include feedlot runoff, land application, or collecting the wastewater in lagoons, which are increasingly threatened under a globally warming planet, under the threats of global climate change, as well as the pressures from regulatory agencies. And so there is and correspondingly, the problem is also evident from the amount of nutrients they release into the environment, especially the soil and the subsurface, as indicated by the nitrogen and the phosphorus load specifically, apart from the other problems like greenhouse gas emissions. All the reds indicate high concentrations of nitrogen and phosphorus in the soil and the subsoil, and it is at the least to say that the soils are saturated when it comes to the amount of nutrients that they can hold, especially in this part of the country, including the state of Kansas. And hence, there is a need to find a solution to this problem. And I wanted to also further accentuate the connection that this problem has to our finite water sources, especially the aquifer out in the west and the high plains, which is the Ogallala Aquifer, and the nitrate concentrations in this finite source might be threatened if we do not manage such large quantities of waste in an effective manner. And so there is an opportunity here, is what our outlook is in this specific context. And it is the opportunities that we can capture and put them all into a circular economy. while it sounds too good to be true, I can tell you that we have actually put some of these into real action. And we'll talk about some of those. But in essence, what a circular economy entails is to capture the carbon as methane gas and effectively use it as an energy source, capture the nitrogen and the phosphorus, and with the intent specifically to produce them into high quality fertilizers, thereby providing a sustainable source in situ or within the local economy where it's needed, and also most essentially capture water for valuable reuse, be it indirect or direct. And this is what we call as a resource recovery platform, which would then enable circular economy concepts to reality in the ag operations and in other sectors, which could be emulated from the outcomes of such studies. Wastewater treatment traditionally has been energy intensive, and this specifically pertains to municipal wastewater treatment while we are talking about livestock waste, but the concepts are similar. The wastewater treatment industry has always employed a high intense load of energy and chemicals to produce only one product, which is basically water. And they have done that very well, but they invest an enormous amount of energy and chemicals to produce only one water. And so the idea is to flip this concept and to be able to not only generate energy and nutrients and water, but to do it in a profitable way or an economically sensible way, and basically make it into a refinery. And to even provide a broader context to it is to look for an approach which will involve holistic opportunities. So this specific graphic might apply specifically to our state of Kansas, as well as to other areas of ag economic dependent communities. So we have ag applications, livestock operations, and communities coexisting. They all generate wastes and the idea is to put them into platform technologies which would just not produce one product, but will produce a multitude of products like water for reuse, slow release fertilizers, and even organic acids for making some of the community-based products. And of course, these platform technologies in the future will receive close scrutiny through techno-economic analysis and life cycle analysis, so they can be considered fit for application into real-world applications. And enter one such platform technology, which we have had great expertise working in the last couple of years. And thanks to the Global Food Systems Initiative, we have had the ability to mobilize some of these into greater utility. And that is the anaerobic membrane bioreactor, which is essentially a combination of anaerobic biological treatment of wastewater, which involves the use of microorganisms that live in the absence of oxygen and convert organic carbon into biogas or methane and carbon dioxide, while they release the nutrients, specifically ammonia and phosphorus, into the liquid. And when it's combined with membrane filtration, which is a physical membrane separation process, the valuable benefit is that the water that is produced is free of any other colloidal or organic interferences, enabling the opportunity to achieve tailored recovery of high quality fertilizers, while the energy is already captured as biogas and also produce water for high quality reuse. And these are valuable and tangible benefits that can apply to the systems that we have been talking all along. So let's enter to the specific project that we are working with, which is the ANMBR treatment of swine wastewater. And this is actually treating actual swine lagoon wastewater from the K-State North Agronomy Farm, where the Swine Research and Teaching Unit is located. And in this farm, they actually have a full-fledged operation, and the waste generated from the swine operations are sent into a lagoon. And there's a great interest from the K-State community, especially the Swine Research and Teaching Unit, which is Dr. Joel Dorochi has been my main person of collaboration, who himself has expressed that they would be willing to reuse the water to high levels and produce and demonstrate these circular economy concepts. So that's the rationale or the background of where the project is set up. And so that's how the swine wastewater from this lagoon looks like. That's just one rapid sample or random sample, but you can see the significant amounts of organic content in it, the ammonia and the phosphate content in it, which of course, when discharged to the environment, not only creates a problem, but then we are also losing the opportunity to not capture these valuable products from this wastewater. And so the anaerobic membrane bioreactor is a compact unit, which might be significantly lesser in footprint compared to a lagoon or any other conventional treatment operation. And we were able to demonstrate successful accomplishment of 80% COD removal and 90% BOD removal. And that's how the treated swine permeate looks like. The color is still there due to the humics, but you can see the rapid and the significant improvement in the quality of the material just by visual inspection. But in terms of the actual removal, is what is being mentioned in the middle of the slide, is that the organic removal has been superior, and it is rich in nutrients, NNP. And the next few slides, we are going to show you how we are going to capture that NNP separately, potentially for valuable use as slow release biofertilizers. And so the proposal for global food systems was trying to demonstrate how we can achieve this nutrient sequestration as calcium phosphate-based products using an electrocoagulation platform, and also characterize plant bioavailability, assessment of the calcium P RNPs for sustainable fertilizer product development. So while the first one was partially completed, mainly because the electrocoagulation unit had its own difficulties, but we have had great success achieving turning that problem or the difficulty we encountered into an opportunity by still demonstrating that we can generate high quality calcium phosphate products, and then also demonstrate that they are available for the plants or potentially plant bioavailable. So we'll go through those results in great detail in this presentation. So let's first talk about the ammonia that was captured onto clinoptilolite clay, which is actually basically a soil particle into which the ammonia can be absorbed into. So we were able to absorb the ammonia, and then we actually conducted, excuse me, a couple of experiments where we wanted to evaluate how these ammonia particles, the ammonia would diffuse from the swine wastewater derived clinoptilolite particles onto which it was absorbed. So we carried out this work in collaboration with Dr. Hetirachi's lab, and we used diffusion testing, which was developed in her facility. And we added the following. We added urea, ammonium sulfate, which are the conventional current fertilizer products. And then we also added the ammonia absorbed clinoptilolite, where the ammonia comes from the swine wastewater. And we also added biosolids, which is another potential fertilizer product that has been used in the field. So what we found was that from the incubation study, we found out that the organic N mineralization increased the inorganic content in all the samples. And the biosolids, interestingly, showed poor mineralization during the incubation period, which indicates that biosolids may not always be the solution while it is currently intensively practiced, right? So there are some lessons to be learned from such an activity. We were able to show that the inorganic N balance was well closed for both the conventional fertilizer products and clinoptilolite. Excuse me. And the results are shown here for ammonium and nitrate. And what we were able to find was the ammonium was predominantly mobilized very significantly first for urea and ammonium sulfate, which we would expect because they are really rapid release fertilizers. But we found out that after 4 weeks, the ammonia was actually gone in all of them, probably because it was either uptaken by the plants or mobilized. But there was still a significant amount of ammonia still left in the clinoptilolite, indicating that it might still be available for release later on during the crop cycle. So it went down by about half. So only 50% of the ammonia was being released, while the remaining was still intact. And the released ammonia was transformed into nitrate, which is another form in which the plants uptake it, indicating that the release is not only happening, but it is actually transforming into the products that are essential for the crop application. So this slow release feature, as captured in these slides, indicates that ammonium that is stored on the clinoptilolite can be available for a longer period of the crop cycle. And so this was actually a favorable feature that we wanted to study. But we then wanted to take it to the next level by applying those products into actual greenhouse experiments, including, and so we used corn crop as the model substrate. And we actually loaded it up with ammonia loaded clinoptilolite. We used either 100% urea or 90% urea, 10% clinoptilolite loaded ammonia, or 80% urea and 20% clinoptilolite loaded ammonia. And then we also did a study with 100% clinoptilolite loaded ammonia, where the ammonia came from the wastewater, right? And then we had control, just soil, no added N. And we analyzed the nitrogen, the carbon, the chlorophyll, the specific activity of nitrogen uptake by the plants, and the pH, so that we can evaluate how effective were these treatments in terms of plant activity. So what we found was actually pretty promising results. We actually found out that the clinoptilolite substitution of urea did not impact the plant biomass. Actually, even 100% clinoptilolite produced the same amount of biomass quality, which was pretty nice and interesting. But please note that it hasn't gone on to the late stage of corn cob production yet. This is 5 weeks study, right? This is after 5 weeks of plant cultivation. But during those 5 weeks, the plant biomass was actually pretty similar between all these conditions. Even more important promising finding was the N uptake, the nitrogen uptake, which is what translates to crop production in terms of the final product like corn, is that there was actually the urea treatment and the 80% urea, 20% clinoptilolite were statistically similar. There was no difference statistically between those two, indicating that we can already start to offset urea application and start investing and putting efforts onto the recovered clinoptilolite-based ammonia products, which is really good. We also tried to analyze if the soil microbial communities changed as a result of these applications, but there was no real difference, indicating that irrespective of the products you apply, whether it be conventional or wastewater derived, the community converges, which is another nice thing that the scientific community will appreciate and know. So the key takeaways from this part of the presentation is that the ammonia sorbed clinoptilolite, where the ammonia was derived from wastewater, is an effective slow end release supplement. The 80% 20% mix of urea and wastewater derived ammonia mix can be used for cutting down potential amount of urea application. And there was no negative impact of treatments on the plant biomass growth and N uptake. Actually, it was similar in condition between urea and that supplemented wastewater derived ammonia. So long-term studies are needed to see if it translates to good yield of the corn crop itself, which will be ongoing in future studies. Now let's shift gears and talk about the phosphorus. We talked about the ammonia. We have about 65 milligrams per liter as phosphorus, which might look low, but in context of wastewater, that's pretty significant. Wastewater has about 6 milligrams, municipal wastewater, but animal wastewater has about 10 times higher amounts than that. So we try to recover this phosphorus, and we actually try to recover it from the ANMB permeate, and we found out that the pH was a big deal. If you do not control the pH, the recovery was very, very vulnerable to change. And we needed a much higher dose of calcium oxide, lime, to achieve higher capture of phosphorus removal. Or we needed much more calcium to recover higher amounts of phosphorus, and it was strongly influenced by the pH. And so we wanted to really start to focus on the initial solution pH and the total alkalinity. And the phosphorus is captured, by the way, as calcium phosphate, which is, again, a similar analogous product that the conventional chemical fertilizer industry uses, which is in the form of triple superphosphate, right? So that's basically calcium phosphates. And so when we analyzed this product, we found out that the total P content was lower than wastewater-derived mineral products such as True White. And not only was it low, the citric acid solubility, which is an indicator of plant availability, was also low. So what can we do? Are there any things? And so we started investigating why it was low. And we found out that we were not producing a lot of calcium phosphate. Rather, we were producing calcium carbonate, which is calcite. And the calcium phosphate was getting diluted. And so we started digging into the problem, and the ultimate solution lies in the carbonate system, where bicarbonate, which is found in wastewater, needs to be controlled and regulated, because at the pHs that we are dealing with, it is probably going to interfere with the ability to capture phosphorus out as a precipitate. And so the first hypothesis was just to increase the pH, get the carbonate out as a precipitate and as sodium carbonate, and see if we can then capture phosphorus. That didn't work. We only got about 65% P removal. So the next approach was to reduce the pH to 4.5 by aeration and then see if that can work. And it worked. That seemed to be the trick. And so our second hypothesis was the one that was a winner. We were able to show that by recycling that CO2 or removing it and reusing it later, we were able to achieve excellent P removal. We got up to 97% P removal actually. And we were able to get to a higher percent P removal even at a low dose of calcium to phosphorus, which was really promising. And so correspondingly, the product P content also improved to be the same as rock phosphate, which is mined for getting phosphorus fertilizers, and even similar or higher than other wastewater derived fertilizer products. And the solubility also went up by an order of magnitude, which was pretty significant. And when we did more analysis, of course, we didn't see much calcite. Instead, we started seeing the hydroxyapatite, which is the main product that we are targeting to produce. And this is just a table that summarizes other technologies that are out there and our study, and it shows that we are either on par or even superior when it comes to P removal. So it's a trade-off between getting the P removed from wastewater, but at the same time also producing a product with high P content. And with Dr. Hetirachi's involvement, we were able to characterize these products even more. We found out that what we had found with elemental analysis or XRD matched with what they found. And they were able to also do further analysis like scanning electron microscopy, which showed similar results, 12 to 13% P, and the calcium that was proportional. And they even went to the next level to do this analysis at the Oregon National Labs using the Zane's device, and they found out that the majority of the phosphorus is in the form of hydroxyapatite, which is a slow release material. And so they further went on to do some incubation studies with soil under neutral conditions, which is important to note. And what they found out was that the amount of plant available P was slowly released compared to the conventional fertilizers like monoammonium phosphate in the middle and triple superphosphate here. And this is the recovered nutrient product, which is basically the calcium phosphate derived from wastewater. And so after 5 weeks, it was clear that the percent resin P started to increase in those different zones while the pH started decreasing. This indicates that the P resin or the plant extractable P from the wastewater derived product is slow release, which is precisely what we were trying to achieve. And the next steps would be to optimize how to tweak that release rate. So we are still able to get the initial rapid growth, but then be able to sustain the release throughout the growth of the crop systems. Now, we have actually submitted a patent based on this novel finding of distributing the CO2 out from the system, because that led us to produce these high quality calcium phosphate products, wherein we are taking the CO2 out of the permeate and putting it back to condition the final water, but then help greatly with the calcium phosphate product production. And so 97% P removal was accomplished and making the water clean, but at the same time, the product that was left behind was of high value too. And so we were able to publish this paper. So the main outcomes of this project include a PhD dissertation, a collaborative research publication with the 2 PIs groups in a chemical engineering journal, and a provisional patent application that has been filed, which are great accomplishments that we want to continue to pursue. And we are also able to submit 2 proposals that are pending, which one of them we hope to hear back soon to see if this will lead us to greater accomplishments. So with that, I would like to acknowledge the grad students, Arvind and Kasuni, undergrad students, Jack and Amy, Swine Teaching and Research Unit, Dr. Joel Derauchi, K-State Facilities, and the Global Food Systems Initiative, of course, which I acknowledged in the first slide. And I want to thank the GFS initiative, Maureen and the team for giving us this opportunity to continue this research mission. Thank you.
Thank you so much, Dr. Parameswaran. And I would encourage anyone that would like to learn more about this project or would like to discuss it in more detail to reach out to either Dr. Parameswaran or Dr. Hetirachi for that discussion. Thank you.